Um, so this is my last lecture. What we're going to talk about today is mutable references. So, along the way, I've been sort of dropping hints that, here's some machinery, step index logical relations. It works in all of these settings, and it scales to features like references. So today, what I want to do is, in the simplest possible setting, I want to show you what some of these complications are that arise when you have mutable references and you try to do logical relations for them. So what I'm doing is basically I'm going to consider simply typed lambda calculus with ML-style mutable references, and I'll come back to that in a second. And then I want to set up basically what's put back up on the board, the basic setup that we had for proving type safety. Okay, so I'm switching back to a unary logical relation, and we're just going to try to prove type safety for mutable references. But this basically demands that the model get more complicated, and I want you to understand the exact details of how. And I think that once you understand this, you can really, most of the work is done in terms of, you can then take it and make it a binary logical relation and talk about equivalence. Okay. So, and I want to try to do this in the first hour or so, and we've already started pretty late, actually. So let's see how this goes. And then I want to spend about 20, maybe 25 minutes just telling you about all of the research out there, a little bit of history of the logical relations, work on step index logical relations that has happened in the last, let's say, 5 years or so. There's been a lot of work. And mostly I'll just be throwing pointers at you, and so you can go look up things if you're interested. Okay, so let's get started. So I have simply typed lambda calculus with booleans, functions, and references. I've thrown in a unit type just because it's sort of a standard thing to have, and I'll get to that in a second. Okay, now, before I even walk through this calculus, when I say ML-style references, what I mean is we want, in our simply typed lambda calculus, now we want to have the ability to dynamically create cells in memory, right? So you're going to have dynamic allocation. We should be able to read out of the cells, obviously, and then we should be able to update them. Okay? So assignment. But when I say ML-style, what I mean is that in ML-style languages in Java, for instance, you only have so-called type-preserving updates, right? Once you create a cell in memory, you cannot update it with a value of a different type. Are people aware of this? Is this confusing? Completely obvious? Completely obvious? Okay, good. All right. And people know why ML and Java have only type-preserving updates? What's the issue? Why don't these languages allow you to manually free memory? Why isn't there a free like we have in C? Aliasing. Xavier had to say it. Oops. Okay, maybe we should talk about it then. Okay, so let's take a very, very simple example. So here's a function f. Maybe I shouldn't write so much on that side. Okay, here's a function f. It takes two references, a ref an x, which is a ref of bool, and a y, which is a ref of bool. Okay? Now, in the body of this function, what I'm going to do is I'm going to allow free. Okay, so first I'm going to go ahead and free x, and then I'm going to read the contents of y. Okay? That's my function. But now suppose that I call this function passing in x and y both pointing to the same memory cell. There's a bunch of memory cells. X and y are both pointing to this one. So at the beginning when I call the function, x and y both point to that cell, and it's true. Then I go ahead and free x. So this is gone. And now I try to read out of y. Oops. Right? Basically, free acts like, there are certain assumptions about the types of these, and you have two aliases, and now you won't be able to prove type safety, basically. This is not type safe. And rightly so. Okay, so languages which allow you to free memory cells or allow you to write a value of a different type into a memory cell over the course of the program, those languages are said to have so-called strong updates. Strong updates are when you can change the type of a cell after it's been allocated. Weak updates or type-preserving updates are when you are not allowed to do that. And languages like ML and Java have this restriction because of the aliasing problem, because you cannot infer things like this, right? You can't always figure out that things are pointing to the same thing. Okay, and just to really drive this point home, I mean, you don't actually just have to free, right? At this point, if my language had strong updates, suppose that I decided to put 5. So I started out with true, and then I decided to write 5 into x. Now it has a 5. And now I want to read out the contents of y, and I'm assuming that y is a reference to a bool. So maybe I read out the contents and then say, then do if then else. Now that's a problem too, right? This no longer contains a Boolean. Okay, so free or a type changing update, a strong update, it's the same problem. Okay, so this is why ML and Java have this restriction that you can only do type preserving updates. And the issue of freeing memory, it gets sent, it's the job of the garbage collector. We assume that once you've allocated a location, it's always going to remain in the heap forever, containing values of that same type. Okay, so it's monotonicity sort of property. Okay, so let's talk about our language. So Booleans, functions, references. The ... over here means we have all of the expressions we had before for the simply typed lambda calculus, right? Abstraction, application, so on. True, false, if then else. I've added unit, which has unit expressions which have the unit type, written 1. We have new, which allows you to dynamically allocate new cells in memory. And we have dereferencing, bang E, read out of a memory cell. And we have assignment, so write some value into some location. And we have locations. So what are our value forms now? It's going to be true and false for Booleans. It's going to be lambda for functions. We have unit values for unit. And what values do we have for ref types? What's the value form? Yeah. Oh. The location, right. Should I stick to purple for a little bit, perhaps? Okay. All right, and then we add evaluation context. We have all the ones that we had before, and now we're, again, just doing left to right evaluation order, call by value. So we evaluate in all of these positions, right? It's a standard thing. Okay, so now let's set up the reduction rules. So in this language, we can't just have an expression E stepping to an expression E prime, right? Because we're allocating memory. So we need a memory or a store or a heap, whatever you want to call this. I'm writing S for store, but people write M, people write H, people write big S, whatever. You're free to choose whatever you want to call it. Okay, and I might actually be switching terminology. Sometimes I say memory, sometimes I say store. But that's what I mean. Okay, so now we have to talk about, the small step operational semantics has to talk about program configurations, right? One program configuration steps to another. So our program configuration is a store and an expression, and it steps to another store and an expression. We take all the reduction rules we had before, and we just sprinkle the S's around, but none of those rules change the store, right? Because they don't touch memory. And then here are our new interesting rules. How do we do allocation, dereferencing, and assignment? So let's just write these out. So I've evaluated my value that I want to put into, right, over here, that I want to put into the store. So how do I actually allocate a new location? Extend the store, so take S and add a new location L to the store, and L maps to V, and new will simply return the location. But here we need an important side condition that we have to pick an L that is not already in the domain of the initial store, S. Right? So we pick a fresh location and we add it to our store. When we want to read out of a location, that location better already be in the store, right? So L is in the domain of S, and basically we want to go read out that value. So the store remains unchanged, and the value that we return will be the contents of the location L in the store. By the way, the store is just a mapping from locations to values. That's obvious to people, right? Everyone good? Okay. All right, assignment. What do we want to do? L better already be in the store, right? So L must be in the domain of S. We want to update it, so we're just going to say in S, put our new value V at location L. So this Here, this is extension, but here, this is just update the contents of L. And for assignment, I'll return unit. You could also just return the location that you've just updated. Doesn't matter. OK, typing rules. If E has type tau, then nu of E is an expression of type ref tau. If E is a ref tau, then reading out of E gives you something of type tau. Assignment, E1 has to be a reference. E2 has to have the right type tau, because it's a type-preserving update, right? So these two types have to match. And then assignment is legal, and it returns, the type checks, and it returns unit. OK, so that's the basics. I'm leaving out recursive types. You could just add it without any changes. But let me ask a question before I go any further. Yesterday, someone said, hey, you just have recursive types in your language. How can you write non-terminating programs? So my question for you today is, Xavier is smiling, can we write non-terminating programs in this language? Yes? So I just have unit, bool, function, and ref. How many people are completely convinced that we can write non-terminating programs in this language? Benjamin's hand going up is like, gives people more confidence, perhaps. OK. So yes, we can write non-terminating programs in this language. And here's a very simple example. OK. This is called Landon's knot. I think it's from the 1960s, 67 or something, a paper of Peter Landon's, OK, where he showed that you could do this. So let's create a new memory cell. OK. X is going to be a new reference, and we're going to put a function of type unit arrow unit into this cell. Okay, so we want to initialize it with lambda z unit. We'll just make it the identity function. Clearly, that has type unit arrow unit, right? Okay, and then we'll say let f be a function that takes something of type unit. And then in the body of that function, we want to read out of this cell x and apply it to this input z. OK, so since this contains a unit arrow unit function, we're giving it a unit, so the body has type unit. So this whole function f has type unit arrow unit. Yeah? OK. And sorry. And then what we want to do is we want to say, let's do an assignment. We're going to take our function f, which is of the right type, unit arrow unit, and put it into this ref cell. And then, semicolon, this means, semicolon. And then we're going to call f with unit. What does this function, what does this code do when we run it? OK, so we have a cell x that contains f. So we call f with unit. All right. So we jump over here, we call f with unit, right? So this disappears, we evaluate this body. So we go and fetch the function that is now stored in x, right? And what's the function that's now stored in f? Oh, it's in x, it's f, right? So basically, when we say fetch the contents of x, we are actually fetching this function itself. So we are, f is therefore calling itself right here and passing in unit. So it'll keep looping forever. Right? Precisely. That's precisely the point of the so-called Landon's knot. Okay? So, so just as an intuition, you have non-terminating programs here, just with just with mutable references. Okay. All right. So. Let's push this up. OK, what we're going to do next is basically edit this unary logical relation that we had for type safety for recursive types, even though I've left out recursive types from the board. But that basic structure, I want to show you how we would need to change it. OK, so I made this explicit yesterday when I was writing on the board over there. I said that the v taus that I've been defining so far what are they? I pointed out that they're really just functions from nat to these sets of closed values, right? So all I'm doing up here in the line is making this explicit for you one more time. Okay, I just want you to remember it. It's going to factor in today. So the way we had built our model of types, the way we had interpreted types until now for type safety, was, we could think of this whole set types as containing type interpretations, I for interpretations, that were functions from these nats to these sets of closed values, right? And we required that these functions be, we required that these type interpretations be downward closed, right? So if a value belongs to a type for k-steps, it belongs to it for less than k-steps. And that's all this is saying, right? If a value is in this set for k-steps, then it's in here for j-steps. Okay? So this was the general, this basically describes the properties that we had for our type interpretations until now. Okay, so what we want to do now is define, we want to extend this with references. So the basic thing that we need to do is define an interpretation for ref tau and say when do values behave like they have type ref tau for k-steps. So what are the values of type ref tau? Thank you. Okay. So when does a location behave like it has type ref tau? Just in English. Okay. Oh, there you are. I was like, where is it? All right. So when it's dereferenced, okay, so when if you have a location, then, yeah, let's think about the ilim forms, right? So Lindsay's saying you want to be able to, when you read out of that location, you want to get a value of type tau, right? And we can look up there, right? When we read out of, the ilim forms for references basically are reading and writing. So, okay, let's extend this so that we, well, how can we say that? Right now we don't have enough information in our model, so to speak, right? To be able to say that when you read a value, when you read something out of location L, if we added a store to the way we interpret types, right? If we started to parameterize these things, so I'll leave the k right where it is, but let's add a store. It looks like we need to have a store in order to be able to say what Lindsay just said, right? In order to be able to say that L behaves like it has this type if the contents of L in the store behave like something of type tau, the type that we expect, for, and I have to put an S here now. And we could put k here or put k minus 1 here because reading out of the store will take one step. So I'll put k minus 1. Okay, so we could do that. So this says, if this were our definition, and it's not our final definition, if this were our definition, this says that a location has this type if whenever you read out of it, it contains something of type tau. Okay, so what about, we only want to allow type preserving updates though, right? So if this is my semantics of references, this tells me what will happen when I read, but how do I ensure that I do the right thing, the thing mandated by the assignment rule? How do I know that I do the right thing when I write into that cell? Yeah?
Some sort of typing restriction on the store?
You have to have some sort of typing restriction on the store, right? So you could annotate locations with type information. Very good. Actually, I forgot to mention something. Let's back up for a second. Let's look at the typing rules up there, because this is very related. I added typing rules for new and ref and assignment. I didn't show you the typing rule for unit, because that was easy. But what else have I just added to my language? Expressions. What's the last thing? Location. And I don't have a location typing rule. Do I need one? Okay, so this is the point that I've been sort of trying to make, right? Though, if you're doing a proof using progress preservation, then yes, you do need a typing rule for locations because, you know, a location is an intermediate term. But if you think about the program as that a programmer writes down, a programmer never writes down an explicit location, right? So if you think about if you think about programs that haven't started running yet, they don't contain any locations. Okay, so expressions that contain free locations are intermediate terms. They arise once you've started running the program. And I've been saying this stuff about, you know, we're doing proofs of type safety in this style where you don't need to type check intermediate terms. So that's why I've left out the location typing rule. If I did have a location typing rule, you know, for those of you familiar with the presentation in TAPL, I think Benjamin uses sigma. So the form of the judgments would have to change. In order to say that L has type ref tau, you need a store typing or a heap typing over here, sigma, that maps locations to their types, right? And here we basically then need to say that, that sigma L is tau, right? But then that's going to change the form of all of our typing judgments. We're going to have to carry around a sigma. By the way, I like to use psi for this, and as you saw, I just made a mistake and I wrote psi again, so I'm just going to switch to psi. To avoid having to repeatedly correct myself. Okay? So it's just a heap typing. All right. So we don't have this. But the intuition for what was psi keeping around? Psi was keeping around, when you do a progress preservation proof, psi is keeping track of the type that every location must contain. Once it's been allocated forever in the future, it must contain that type. Right? And that's kind of a type of information we're missing here. We want to be able, this model needs to be able to track what location, what type a location will contain forever in the future, right? Now, so what I'm going to do here is I'm just going to get rid of the store S here and instead put in a psi. But my psi is not a mapping from locations to syntactic types. Okay? It's going to be a mapping from locations to semantic types, which are these kinds of things, these type interpretations that we've been building. Okay? All right, so let's see how that affects things. So now, if I, and by the way, I erased the S here, if that's confusing to someone. I'm going to make changes to the rest of the model to make sure that wherever in the definitions we have to actually run something, we pick a store. We're going to pick a store that satisfies psi, and so everything will be okay. All right, so the store doesn't really need to be part of this part of the model. Okay, so how do I change this definition now? So now a location behaves like it has type ref tau if my heap typing or store typing says that it should have type ref tau. That should basically be the intuition, right? So let's see. So basically, psi of L something like that. Right, because I said that my psi is mapping locations to semantic types. Someone have a problem with what's on with this definition? Do we need to use a step indexing on the V? Right. So the definition as written, we're defining interpretations of types at step level K, but we seem to be using something bigger, right? And our primary induction is on K. So let's see. Right. And the way I should do this is we want to say psi of L. So psi of L is one of these i's, which is now not just going to take a nat. It's going to take a natural number for the step index, but it's also going to take a store typing, right? So we need to come back and edit this part of the definition. All right? But let's hold that thought for a second. And then we want to say that here you want to use essentially some sort of k minus 1 psi type of thing, right? And you want to say that that is equal to the interpretation of v tau, and again here we want a k minus 1 psi kind of thing. People with me or people getting lost? Okay, so here's the basic idea. I haven't formalized it yet. It's still not yet the final, or at least I haven't told you enough to make sense of what I've put up there. And yes, it's not the final definition. Okay, but it's very, very, very close. Here's what we're doing. Okay, so before, by the way, the things these models that we're building, the step indexing trick, these are essentially what are called Kripke models or possible worlds models. How many people are familiar with that term? Okay, very good. A lot of you. All right. So so Kripke models are normally built from modal logic, where there's this notion of saying that something is true, not always. So just by analogy, initially we started saying that V looks like it has type tau, but then we finessed this a little bit and started to say, oh, we don't want that notion. We want the notion of V behaving like type tau to be relative to the world that we are in. And that's where the term possible worlds comes in. So the world that we are in is in this model was being characterized by the number of steps that we have left to run. And now what we're doing is we are enriching our world. Now the world that we are in is described by how many steps we have left and what the shape of our heap is. Okay? So stay with me. All right. So basically now we're saying that values behave like they have some type relative to some world. The pair of the k and the store typing, the semantic store typing, is our world. Okay. And of course, just like we were making sure, well, just like before, we were making sure that we always appeal to things in the definition at a lower step index. We're doing the same thing. Now, the important thing is editing the definition of type over here. I'll say that psi is drawn from some space that I'll call store type. Psi is a store typing. Okay? So now our type interpretations take a world, which is a pair of a step index and a psi, a store type, and give us sets of values that belong to that type. Okay. And what is a store type? So a type is not cross. Oh, I can't erase that. Let me know if I start writing too small. Store types psi are just a mapping from locations to semantic types, right? And semantic types are these things. So this is just a finite map from loc to type. Yeah? Is there anything wrong with this? Types depend upon store typings, and store typings depend upon types. It's circular. But is it really a problem? Well, let's sort of see if this space could possibly be well defined. We could do a simple cardinality argument. So this equation says that the cardinality of the set type is strictly greater than the cardinality of store type, and this says that the cardinality of store type is greater than or equal to the cardinality of type. Okay, therefore the cardinality of type is strictly greater than the cardinality of type. Okay, so this is a problem. So we need to do something, right? Okay, so what we're going to do is use step indexing to stratify these sets. Okay, so what we want to do is at type level 0, we'll just say type is, think of it as just an empty set. All right, and then at type level k plus 1, I'm just trying to express intuition for now, or formalize in a second. At type k plus 1, we only want to depend on store typings from level k. And then we'll say store typings at level k only depend on types at level k. All right, so we've broken the circularity right here by going down a step. All right, now we're good. Yes?
The same thing that we do. How many steps of evaluation are left?
Yes, I mean, I could have written n here because right now I was just trying to make an informal argument about the stratification that we are interested in. But yes, it should be that. But let's try to formalize it.
Then should we include something like the map that's passed to the first
Right,
one?
that's why I was saying that, this case. So when we try to define these sets, we need to be a little bit more careful. So let's call, I'll rectify this. Let's call these things a pair of a step index and a store typing. Let's call them worlds. Okay. Really should be putting world above type. I don't have space. So it'll have to go here. So we're going to say that a world at level n is just, let's see, sets, I'll write W, that are a pair of k and psi. Oh, I need to erase this, if that's okay. At least a little bit of it. Okay, so what we're going to say is worlds at level n only contain k's that are strictly smaller than n. I hope you've got this intuition here because it needs to go. And then we need to say something about this psi. This psi only needs to be drawn from this k. So there's a sort of dependency here, right? So we need to say that psi belongs to store type k. And this is precisely what Benjamin was just pointing out. The step index that we use, this psi constrains the level of the psi that's sitting right next to it. Okay, so every time we put this k psi subscript on our type interpretations, we will always assume that if you have a k sitting here, then the psi is drawn from the set store type approximated to level k. Okay? All right. Now, that's my world. What is store type? So now we want to say that type at level n is drawn from world n. So it's a mapping from worlds at level n to these sets of values. And I'll edit the rest of the definition in a second. It's not correct, but let's just get our sort of meta-level types right. And we want to say that a store typing, as before, it's a psi is a mapping from finite map from locations to types, but just like I wrote in the equation there, we want store type n to be drawn from type n. Okay, so I've broken the circularity in precisely the way that I was sort of alluding to before, all right? But the actual mechanics of it is right here. A world at level n contains step indices here that are strictly smaller than n. All right? Okay. So everyone good with this? Any questions? Okay, so now let's go back and look at this. What was I trying to do over here? Well, remember we just said that worlds are sort of well-formed. If whenever you have a k here, this psi has to be drawn from store tie k. Well, okay, so we start out with a well-formed world. Psi belongs to store tie k. We have a k here. But this isn't quite right. The psi still belongs to store tie k, but now we have a k minus 1 sitting over here. So we need to do something to approximate, to sort of lower the level of that psi. And I'm going to write that as to do that there and here. So just making sure that my worlds are well formed throughout the model. All right, and I'll define that approximation in a second. Or maybe I should define it right now. Okay, let's define approximation. So an approximation of any type interpretation, because actually, let's do psi first. Psi approximated to level k is just all the locations that you already had in psi. Psi L is equal to I. Then this is going to be, you just take the range and approximate that. And the way we define approximations of type interpretations is we say that, well, basically we just want to restrict this function to level k. So maybe I don't even need to go to that trouble. I'll just write this as take this function I and restrict it to world at level k. Restriction. So in other words, whatever the function tells you about levels k plus 1 and higher, just ignore that. Okay?